Now let's understand how this resting membrane potential is actually generated. As I have mentioned that many potassium channels is responsible for the generation of resting membrane potential and very few sodium channels is open. So majorly we will focus on the potassium channels. So I have mentioned previously that the sodium potassium pump actually generates this concentration gradient, ion concentration gradient. We call it ion concentration gradient, and this is the chemical force, because I have mentioned that channels actually move ions from higher to lower concentration. So if there is no ion concentration gradient, there will be no movement of ions through the channels. So the background is actually established by the ATP driven pump like sodium potassium pump. So the chemical force is first point we have to understand. Now the second point comes the electric or membrane potential or electric force. What happens here? When the concentration difference is present, the open channels will actually export more potassium from inside to the outside, because inside is higher concentration, outside is lower concentration. But at some point or some point of this membrane potential, at some value of this membrane potential, as because more potassium ions are actually accumulates in the exterior, that will repel further movement of potassium from these channels. So at some value, suppose here I have mentioned the value generally is minus 70 millivolt. At this membrane potential, the potassium ions are present in the outside will repel the further movement of potassiums. That means there will be no net movement of potassium occurs. So at minus 70 millivolt, scientists found that no net movement occurs. No net movement of ions occur. Now this is not only for potassium ions but for all ions. So in resting conditions or unstimulated conditions, cells do not actually show net movement. Now no net movement doesn't mean there will be no movement. No net movement means if at this membrane potential minus 70 millivolt, if 100 potassium comes out, 100 potassium will come inside. The similar is true for sodium also. If 10 sodium comes in, 10 sodium will come out. That means by the movement of ions, there will be no further change in the membrane potential. This is very important. That means no net movement occurs at this point, because this force, electric force, will actually prevent this chemical force. So electric force will prevent the chemical force, and at some point, like here the point is minus 70 millivolt, the electrochemical gradient, the together value will be 0. So there will be no net movement of ion occurs. Another point we have to understand, this resting membrane potential is also called equilibrium potential. Equilibrium. Because in that potential, the two forces actually equilibrate, balance each other. So it is also called equilibrium potential. During this generation of resting membrane potential, the concentration difference or ion concentration difference does not change significantly. So ion concentration gradient of ions not change significantly, or actually do not change. Why? Because a very small amount of movement of ions, here I'm giving example of potassium, is just enough to make it the resting membrane potential. So don't confuse that during this transportation of potassium or sodium, the ion concentration changes. No, very small amount of movement of ions can establish the resting membrane potential. So we have to understand 3 points. The first is, during this resting membrane potential, no net movement occurs because the ion concentration gradient, the chemical force, is actually neutralized by the electric force. As because more potassium ions accumulate, so that actually prevents the further movement of potassium ions, and that difference in the voltage, if you put 2 microelectrons, you will get 70 millivolt. Then it is called equilibrium potentials, and here from we will actually derive one equation called Nernst equations. Nernst equations, which is very important, and from this equation we will get a value, very close value of minus 70 millivolt from this Nernst equations, and this is called electric potential, equilibrium potential. And another point you have to understand, that during this resting membrane potential generation, ion concentration gradient do not change. Okay, the first thing we have to understand that Nernst equation is derived from these two forces. It is actually getting the two value. Suppose the free energy change for this chemical concentration gradient, and if you add the free energy change for this electric force, we will get the value of 0 at equilibrium potential or this resting membrane potential. So at the resting membrane potential, the free energy change by this chemical force and electric force will be 0. Now the formula for delta G for the chemical concentration is minus RT ln the concentration of, I am giving here example of potassium, as I have mentioned, the potassium ions is important. So potassium ions in the outside, so I am writing here exterior, and the concentration of potassium ions in the cytosol. So this is for the free energy change of this chemical force, and if you add the free energy change of electric potential, it will be the equilibrium potential. Remember this is the value of equilibrium potential of the potassium ions, and ZF, that is actually is 0. Now what is R? R is the gas constant, T is absolute temperature at degree Kelvin. The value of R is actually approximate 2. The T, that means absolute temperature, is actually at degree Kelvin. So basically the degree centigrade is actually added with 273 value. So if there is 37 degrees centigrade in the cell, we will add another 273 to get it Kelvin scale. So it is about 310 Kelvin. So we will writing here 310 Kelvin, degree Kelvin, that means 37 degrees centigrade. And the Z means is valency. The valency for potassium is +1, and the F is Faraday constant. The Faraday constant is 23,062. If we exchange this value, we will get this formula. This EK, or equilibrium potential of the potassium ions, is equals to RT by ZF. Now if we convert this natural logarithm, we have to add another value called 2.3, then it will become log value, and here the potassium ions in the exterior concentration and the potassium concentration in the cytosol. So if we put this all values, we will get 2 into 310 divided by 1 into F, means 23062 into 2.3, and this log value of exterior is potassium is 5 millimolar divided by 155 millimolar. If you calculate this all value, you will get this value is 0.061, and this value will be such that the total amount of these equations will be minus 98 millivolt. Okay, so if you multiply this and if you put this value, you will get 98 millivolt. Why the value of resting membrane potential is less than minus 98 millivolt? Because few sodium ions channels are actually open, and what will happen, as because sodium ions are higher in outside and lower inside, so more sodium will move inside, and that will actually decrease the value. So as you can see, the value should be minus 98 millivolt if only potassium channel is responsible for the generation of resting membrane potential. But as because few sodium ions are actually involved in the resting membrane potential, so the value will drop because more positive ions are actually coming inside. That's why the value of the resting membrane potential actually comes down into minus 70 millivolt.